In this video, we'll review how to do limiting reagent experiment calculations.
In order to process your data for the limiting reactant lab, you need several pieces of information. The first of which is a chemical reaction equation that accurately describes your reaction. Here we have the beginnings of a reaction equation that are given to you in your lab manual, and it contains the reactants, sodium bicarbonate and citric acid, and then the products on the right-hand side, which include carbon dioxide gas, which is what we see as bubbles in our experiment. So in order for a reaction equation to be accurate, it needs to follow the law of conservation of mass, and that says that whatever atoms we have in our reactant side, we have to have the same number and types of those atoms on our product side. So the first thing we do is check if that's the case. And so we count the number of atoms of sodium, of hydrogen, carbon, and oxygen on each side. On the left-hand side, on the reactant side, we have 1 sodium, 7 carbon, 9 hydrogens, and 10 oxygens. On the right-hand side, we have 3 sodiums, 7 carbons, 7 hydrogens, and 10 oxygens. So what we can see is that we have a case where we have 2 atoms that are out of balance. We have more sodium on the product side than we do on the reactant side, and we have fewer hydrogens on the product side than we do on the reactant side. So the way we begin to deal with this is by putting coefficients, which we call stoichiometric coefficients, in front of the chemical formulas to add more sodium atoms to our reactant side. So we have too few sodium atoms on the left, so we're going to start balancing our equation by adding a 3 so that the sodium atoms are in balance. So we add that coefficient, and then we calculate how many of each atom type we have. So now we have 3 sodium, 9 carbon, 11 hydrogens, and 16 oxygens. If we look on the right-hand side, we have balanced the sodium, okay, but now we still have the carbons are now no longer balanced, and we have the hydrogens are not balanced, and neither are our oxygens. So the next thing we're going to do is we're going to try to balance the carbons by adding a coefficient in front of the CO2. So we can balance the carbons, okay, by adding a 3 in front of the CO2. So let's tally our atoms and see where we are. So we've got 3 sodiums, 9 carbons, 11 hydrogens, and 16 oxygens on the left. On the right, we have 3 sodiums, 9 carbons, 7 hydrogens, and 14 oxygens on the right. So our sodiums and our carbons are now balanced, but our hydrogens and our oxygens on the right-hand side are now fewer than they are on the left-hand side. So we'll need to add a coefficient to adjust these, and conveniently we have one compound in our reaction that contains both of those elements and none others. So if we're able to balance by putting a coefficient here, we won't knock these out of balance. So next step, I put a 3 in front of the water, and so now I have on the left-hand side, I have 3 sodiums, 9 carbons, 11 hydrogens, 16 oxygens. On the right-hand side, I have 3 sodiums, 9 carbons, 11 hydrogens, and 16 oxygens. So I have the first key piece of what I need to process my data. I have a balanced equation, which you see down here. Okay. The other piece of information I need is the molar masses of my compounds of interest. So my sodium bicarbonate molar mass is 84.007 grams per mole. My citric acid is 192.124, and my carbon dioxide is 44.01. And the reason the carbon dioxide is of interest to me is because this is the product that we measured when we measured the mass of everything before and then the mass after the reaction, because the carbon dioxide floated away. So we can assume that the mass that was lost was the mass of the carbon dioxide. Okay. All right. So now what we're going to do is let's take some sample data and try to figure out if who is the limiting reactant. Okay, so a limiting reactant is the one that that limits how much product you can make. So if you imagine you're making sandwiches and you need 2 pieces of bread. So these are my bread, and let's just say I'm making cheese sandwiches. All right, so that's my bread. And let's say that I have 7 slices of bread, and I've got cheese, and so my cheese, I'm going to have 1 big thick slice of cheese per sandwich. And let's say I have 9 slices of cheese. Okay. So 1 sandwich, right? Oops. Let's make that one word. It uses 2 slices of bread and 1 slice of cheese. So, if I'm starting with these materials here, how many sandwiches can I make? Well, let's count, right? So, I've got 2 slices of bread and 1 slice of cheese here, right? 2 slices of bread and 1 slice of cheese here. So that's my second sandwich. My third sandwich, 2 slices of bread and 1 slice of cheese here. Okay? And so, as you can see, okay, I'm going to have some of my material left over. I'm not going to be able to use all of my material to make sandwiches, right? In this case, okay, the thing that is limiting how many sandwiches I can make is the bread. I run out of bread before I'm going to run out of cheese. So if I had 1 more piece of bread here, I'd be able to make 1 more sandwich, but then I'd still have a lot of cheese left over. So in this example, okay, bread is what we would consider the limiting reactant. Okay. If I were to write this as a chemical reaction, I would say 2 slices of bread plus 1 slice of cheese produces 1 sandwich. Okay. And these numbers right here are equivalent to my stoichiometric coefficients in my equation. When there is no number in front of your chemical, you can assume that that number is 1. Okay. So these are our stoichiometric coefficients. And they tell you how many molecules or how many moles of molecules are going to react. So 3 moles of sodium bicarbonate reacts with 1 mole of citric acid to make 3 moles of carbon dioxide. Okay. So if we want to figure out the limiting reactant, we have to figure out how many moles of each thing we have and which one is going to limit how many sandwiches we can make. So let's put some numbers to this and do an example using our information. I'll switch to blue for our example. All right, so let's imagine that we have, that we did an experiment where we took 0.52 grams of sodium bicarbonate and we took 1.10 grams of citric acid. And what I want to know is which is the limiting reactant. All right, so in order to make product, I have to have 3 times as many molecules of the sodium bicarbonate as I have of the citric acid. So let's figure out first how many moles we have. So number of moles of my sodium bicarbonate is going to be equal to my mass. And I'm just doing a unit conversion from grams to moles, right? And I want it to equal moles. So the moles is going to be on the top, grams per mole, and my mass, 84, my molar mass, 84.007 grams is going to be on the bottom, right? And so when we take 0.52 and we divide it by 84.007, okay, that means we've got 0.006 moles of sodium bicarbonate. Okay. And now let's look at the number of moles of our citric acid. So we've got 1.1 grams, and we're going to divide that by its molar mass of 192.124 grams per mole. So we've got 1.1 divided by 192.124. And so I have 0.0057, or let's round 0.006 moles of citric acid. And this is very funny that those numbers came out to be the same because I just picked these masses off the top of my head. Now, so we have an equal number of molecules of these two things, but remember that I need 3 times as many sodium bicarbonate as I do the citric acid to react. So let's figure out how much product we can make in terms of moles, okay? So from each of these, right? If I use up and react all of the sodium bicarbonate, okay, 0.006 moles sodium bicarbonate, and what I want to make is my product, a mole of CO2. I'm going to put my moles of CO2 here and my moles of sodium bicarbonate down here, and I'm going to use my stoichiometric coefficients. So I can use 3 moles of sodium bicarbonate, and that will produce 3 moles of carbon dioxide. Okay, so from that amount of sodium bicarb, I could make 0.006 moles of CO2. Let's see how much I could make from the amount of citric acid I have. Okay, so I have 0.006 moles of my citric acid. And I know that I'm going to make 3 moles of CO2. How many moles of citric acid does that take? We're going to go back to our equation and look at the stoichiometric coefficient, and it's a 1. Okay. So this is going to give me a different amount. All right, so 0.006 times 3 makes 0.018 moles of CO2. So what this tells me is that I have enough citric acid to make this much CO2, but I only have enough sodium bicarbonate to make 1/3 that amount, 0.006. Okay, so what we can deduce from this, okay, is that sodium bicarbonate was the limiting reactant because it's the thing that when it's totally converted to product, okay, produces a smaller amount of product. So sodium bicarbonate is the limiting reactant. Now, if I want to figure out, if I started with these amounts, okay, how much CO2 could I make? Okay, I would take the number of moles that will occur, or that will be made when I've used up all of my sodium bicarbonate. So this is the maximum amount of carbon dioxide I can make when I mix these two amounts of things together that are shown here. So now the last thing we're going to do, okay, is how much CO2 can be made from these starting materials. And we want to know in grams, okay? Because that's what we can measure in the lab. So we've already figured out that we can make 0.006 moles of product. And so what we want to do now is convert that into grams of CO2 by using the molar mass. And so we have the molar mass of CO2 up here. It's 44.01 grams per mole. 44.01, we put the grams on top because that's what we want, the unit we want to wind up with. And so our moles will cancel, and we will wind up with 0.006 times 44.01, and that winds up being 0.264 grams of CO2. So if I were doing this experiment, and this is the material that I started with, when I weighed my beaker at the end, it would have lost 0.264 grams of mass. In the example that we've been looking at, we've identified first that sodium bicarbonate was the limiting reactant, which, if we go back to our sandwich example, tells us that our citric acid, since it was not the limiting reactant, is like the cheese. And after I have reacted all my limiting reactant, which in this case is either the bread in our sandwich example or the sodium bicarbonate in our chemical reaction, the non-limiting reactant, here the cheese and the citric acid in our experiment, will have molecules left over unreacted. So we are curious as to how much citric acid will be left over after we react all of our sodium bicarbonate. Okay, so how much of the citric acid, so the non-limiting reactant, or we would call it the excess reactant, is left over and unreacted at the end of the experiment. So here what we're going to do is we're going to start by looking at how many moles there were of the limiting reactant. Okay, so if we look here, our limiting reactant was a sodium bicarbonate. Okay, so this is the amount of the limiting reactant. So that's this right here. So let's start with that. That's how much we had to react with. 0.006 moles sodium bicarbonate. Now the next thing we do is we're going to go back up and we're going to look at the reaction stoichiometry. We're going to look at the relationship between how much sodium bicarbonate reacts with how much citric acid. Okay, so this ratio of 3 to 1 is the equivalent of in our sandwich of the 2 pieces of bread to the 1 piece of cheese. Okay, so we're going to use the ratio of these things as a conversion factor for us to figure out how many moles of citric acid. So we want moles of citric acid. How many moles of citric acid is going to react for, each mole of sodium bicarbonate. And we're going to use those stoichiometric coefficients from our chemical reaction. So we have 3 moles of sodium bicarbonate, so that will go down here on the bottom, for every 1 mole of citric acid that reacts. So this is going to tell us the number of moles of citric acid. And when we do this math out, we get 0.002 moles of citric acid will react. Okay. So now how much mass is this? Because the mass is what we can measure in the lab. Okay, so that we just have to convert our moles of citric acid to grams of citric acid. Okay, and so we would use our molar mass here, which for citric acid is 192.124 grams per mole. 192.124 grams per mole of citric acid. Oops, sorry. So in this case, okay, our moles will cancel and we're going to be left with grams of citric acid. So that gives us 0.384 grams of citric acid reacted. Okay. So now, how much of our starting material is left over at the end of the reaction? And that is our final question. So we started with, in this case, we started with 1.100 grams of citric acid. So 1.100 grams of citric acid. And so we're going to subtract out the amount that reacted, minus 0.384 grams of citric acid. Oops. And so that tells us that we're going to have 0.716 grams of citric acid that remains unreacted at the end of the experiment if we're only reacting it with 0.52 grams of the sodium bicarbonate. So in that beaker, okay, there would be this much citric acid left over. And the point of the confirmatory tests is to test, that prediction that we have unreacted citric acid. So we could add sodium bicarbonate to a beaker, and again, if there's leftover citric acid in there, a reaction will occur and you'll see bubbles. So that's how to determine how much of the excess reactant is left over. And that's how you do the calculations for limiting reactants.